Hi. In previous videos, we've learned how to calculate determinants, and we learned a Laplace expansion, which is also a way of calculating determinants. Now we're going to review some properties of determinants that will actually allow us to deal with the determinants with bigger ease. Okay, so property number one. Interchange of rows and columns of the determinant does not affect the value of determinant. Okay, look, basically, what does it say is that if I'm going to take, if I'm having matrix A, and I'm going to calculate its determinant, and I'm having some matrix, transpose matrix A, and I'm going to calculate the determinant of this transpose matrix, those values will be the same. Okay, let me illustrate this with an example. Okay, if we have determinant A, B, C, D, let's just say that this is determinant A. Now, transposed, if I'm going to calculate it, this is going to be AB minus B, C, right? Now, if I'm going to take transposed determinant, I would have AB, CD, right? This is AB minus BC. Okay, so look, this property is very simple, but it's what are the implications of this property we will be discussing a little bit later. Okay, now property number two is the interchange of any two rows or columns will alter the sign but not numerical value of the determinant. Okay, let me again show you how this property works. Again, we can start with determinant A, B, C, D. And look, we know, of course, that this is AB minus BC, right? But what if I'm going to take and let's denote what if I'm going to take and switch the rows over here. So I'm going to have a CD, A, B. Okay, if I'm going to multiply this, I'm going to get BC minus AB. But this is the same as negative AD minus BC. So this is minus AB, C, D. So, what this property is showing us is that if you exchange places of any two rows or columns inside the matrix, you will get the same number in absolute value. but the sign will change. Okay, now let's go to property number 3. And it goes like this. The multiplication of any row or column by a scalar k will alter the value of a determinant k-fold. Okay, again, it can be really easily explained. Look, we started with determinant a, b, c, d, and we know that this is equal to ab minus bc. Now look, what would happen if now I would multiply first row, for example, by any number, constant number k. So, I would have here ka, kb, cd. Okay. Now, if I multiply it all out, I get that this is KAD minus KBC. I can take K out of the parenthesis. And this is just K times A, B, C, D. Okay, this property of the determinant is extremely important because it allows us to do something called factoring out. So look, we can take any number from a given row or a given column. Let me show you this with an example. Okay, let's just start that we've got 15, 7, 12, 2. Okay, look, I know that even now this is relatively easy to calculate, but we can make all the calculations here simple. How? Well, look, I can take a common number out of any row or any column. What can I do here? For example, I would like to take 3 out of the first column. So, if I'll do this, I'm going to have 5, 4, 7, 2. But look, I can simplify this even further. Because out of the last row, I can take also 2. So I will have 3 times 2 times 5, 7, 2, 1. Which gives us 6 times 5 minus 14. So this is 6 times negative 9, which is equal to negative 63. Okay, and again, this is extremely useful property when you calculate big determinants and you want to make your calculations simple. Okay, but now that we've dealt with this property, let's move to property number 4. Okay, so we've got D. Oh, you know what? One more thing. Look, we should notice at this moment that multiplying the matrix or multiplying a determinant by a number is a completely different thing. So, but matrix versus determinant. Let's let's know this very simple thing. Look, matrix, as we said, is a table. Right? This is a table filled with numbers, parameters, variables. It is a table. Determinant is a number, is a scalar, is just one number, even though at some stages of calculations it appears to look like a table. And now look at the other thing. If I have matrix 1, 2, 2, 4, for this matrix I can calculate determinant by like this. But now look, there will be a very big difference between multiplying matrix by a number. Because look, if I multiply a matrix by a number, what am I getting? Multiplication of a matrix by a scalar is multiplying each element within the matrix by this number. So I will get 2, 4, 4, 8. But what now would happen if I would multiply determinant by a scalar, 2, okay, make it simpler. Okay, I can get here 4 possible different cases. It will be, I can get 2, 4, 2, 4, right? But this would be the same as getting 1, 2, 4, 8. Or this could be the same as 2, 4, 2, 4. And finally, this is the same as 1, 2, 2, 8. So look, remember, there's a big difference when we multiply matrix by a number and we multiply all the elements, and when we multiply a determinant by a number, where we need to just multiply any row or any column. Okay, but so now we can finally go to property number 4. And this is another extremely useful property when we calculate complicated determinants. And it goes like this: the addition or subtraction of a multiple of any row, or of course column, will leave the value of the determinant unaltered. Okay, so again, we start. What does it mean? Look, we know that A, B, C, this determinant will give us AB minus BC. And now look, what if I would take entire first row of this determinant, I would multiply it by any number k, and then I would add it to the second one. Look, what we would get as a result is A, C plus A, K, B, D plus A, K. Okay, now let's calculate it all out. I'm sorry, BK. Okay, now we get that this is AD plus ABK minus BC minus ABK. Those two cancel each other out. AD minus BC, which is simply ABC. Determinant ABCD. Okay, so as you see, this is extremely powerful property. It actually tells us that we can take any row or any column, multiply it by any number, add it to another row or a column, and we will get the same value of the determinant. This is another way of, look, how do we usually use it in math problems? We use this property in such a way that, for example, imagine something like this, that you have a determinant in which you have 1, 2, 4, right? Now look, if I am going to multiply this row by 2 and subtract it from this row, what will I get? And of course, right away, we can see what the result of calculation will be, because if we have either full row or full column of zeros, the result must be 0. Okay, and now property, now let's go to property number 5. And property number 5 goes like this. If one row column is a multiple of any other row column, the value of a determinant is 0. Okay, first, how do we get this? Look, if I have, for example, that here I have AB, and here I have KB. So we see that actually those two rows have very clear connection between it. Because if I multiply this row by K, I will get this row. Now, if I'm gonna calculate it all out, I'm gonna get that this is KAB minus KAB. This is gonna be 0. So, we clearly see that if there is a strict proportion between any two rows, or after some operations we can show that two rows or two columns are identical, value of the determinant must be 0. We don't need to calculate, we just know that it must be equal to 0, and we don't even need to calculate anything. Okay, so knowing this, let's go back for a second to matrix inversion. Remember, a couple videos ago, we were talking about matrix inversion. We actually use determinants as one of our tools that will allow us to invert a matrix. Why is this? Now that we know some properties of determinants, we can go back. To this matrix inversion, and we can notice a couple of things. So, look, if we have some square matrix A, then, look, we is different than 0, then transpose determinant will also be different than 0. But if it happens to be that A is equal to 0, then we can be sure that transpose determinant will also be equal to 0, based on property number 1 that we've discussed, right? But look, looking at the fifth property, we see that when do we obtain value of 0 in the determinant? Well, we obtain value of 0 when we have when there is a connection between the two rows, when I can simply express one row of a determinant, as a multiple of another. So look, in this case, we can say that those rows are independent. So okay, let's write here we have row independence. And we see that this row independence is actually implying column independence. Okay, and here's the opposite. If we have row dependence, we have, this implies column independence. Column dependence. But look, I could again transpose this determinant, and I would get the result that from column independence I could get to row independence, and the same from column dependence I could get row dependence. So we see that we get this outcome that the value of the determinant is 0 is when two rows of a matrix are somehow connected. Have we seen it somewhere? And look, again, let's go back to the video about matrix inversion in different types of simultaneous equation systems. Look, basically, if we have system y equals to ax plus b, y equals to cx plus d, and those two are different numbers, right? We will get that those two functions, linear functions, that can, of course, give rise to system of simultaneous equations in the form we'll have one unique solution, right? But in the case where we have y equal minus ax equals to some b, y minus ax equals to some d, we will get either no solutions, or in a special case where d and b are equal to each other, we will have infinite number of solutions, right? And you see here clearly that here we have, when I will calculate matrix of coefficients here, 1, 1, a, there is a row dependence, right? I can, of course, I can mask it. I can mask it in really different ways, because I can multiply this equation by k, but it doesn't change anything. Here we would have k, here we would have k. But look, if I'm going to calculate determinant for this expression, I will still get ka minus ka, and it is equal to 0. And look, in this last property, we got the entire reasoning behind the connection between determinant and between determinants and systems of simultaneous equations. And now look, we can now very nicely summarize our conclusions, because we get that if A is different than 0, we have what? Row or column independence. Right? But this, in turn, this also gives us that A is not non-singular, and because A is non-singular, we can say that inverted matrix A exists. And now there is a very important point. Assuming that vector D is different than 0, because if by this I mean that at least one element of vector D is different than 0, then system of simultaneous equations in matrix notation will have one unique solution. Okay, so look, we've learned how to deal with the determinants. We've learned about their properties. We've learned how those properties connect to system of simultaneous equations. And finally, we were able to see that if determinant is different than 0, we have row and column independence. A is non-singular. We can invert matrix A, and assuming that this vector D is not made out of only zeros, because this is the homogeneous system of homogeneous equations we will do in the future. In this circumstance, we will have one unique solution. And look, this actually provides us with very simple test whether a given system of simultaneous equation has a solution or not. How do we do it? We write it into matrix form. We calculate the determinant of a matrix of coefficients. And once we have established that this determinant of matrix of coefficients is different than 0, it means that the system of simultaneous equations has one unique solution. Okay, and basically we are almost ready to start dealing with matrix inversion and finding a solution to any system of simultaneous equations. But before we go there, we just need to learn about one more property of determinants, and this property is called expansion by alien cofactors. Okay, and this property goes like that. So here we have property number 6. The expansion of a determinant by alien cofactors so those are cofactors of a wrong row column always yields 0. Okay, so how does this property work? Okay, this property, okay, let's illustrate it again with determinant A11, A21, A31, A12, A3, A22, A23, A32, A33. Okay, look. When we did Laplace expansion, we were doing it like this. Let's just say that I'm going to use this row. And how were we going about it? We were using A11 times C11 plus A12 times C12 plus A13 times C13. Right? So each consecutive element, so each element is multiplied by its cofactor. But look, what if I do it a little bit differently this time? What if I'm going to use cofactors not from the first row, but I'm going to be using cofactors from the second row while I'm using elements from the first row. Okay, so what would change? Well, those cofactors here are gone. And I'm going to use cofactors from the second. So I'm going to get C21 plus A C22. And here we would have C23. Okay, now let's see what am I going to get after the multiplication. Okay, so I got A11 times cofactor C21. So for this element is in the second row, first column, and cofactor for this, we get is A12, A13, A32, A33. Right? Now, I'm gonna get A12 and what? Cofactor C22, so cofactor for this element, right? So now I'm gonna get that this is negative 1 to the power 2 plus 2 times, I delete second column, A11, A31, A13, A33. Okay, and finally the last one we get A13, cofactor negative 1 to the power 2 plus 3. And over here I will have A11, A12, A31, A32. Okay, so we clearly see that here we're going to have a minus in front of A. Here we're going to have plus, so we can get rid of this. And again here we're going to have a minus. Okay, now let's calculate this all out. Okay, so out of this we're going to get negative A11, A12, A33 plus A11, A32, A13, right? Then out of this one we will have plus A12, A11, A33 and minus A12, do we see any resemblance? Oh, I see one here. A11, A12, A33, A12, A33. They have the same values, opposite signs. Now, any other? Oh, here. This one is exactly the same as this one. And finally, I can clearly see that those two are also identical. So, we cancel each other out because they have opposite signs. What I come up with at the end is 0. And look, basically, this is how the entire idea of the expansion by alien cofactors work. We can see over here. We can see over here that if I want to do expansion by alien cofactors, what am I doing? I'm taking cofactors from elements from one row, cofactors from a different row, and as a result, I am getting 0. Ha! Why is this happening? Look, because as it turns out, if I would be using, look at all those that we've calculated. As it turns out, if I would take a slightly different determinant and similar determinant to the one you see over here, so A11, A12, A13, A11, A12, A13, A31, A32, A33, and I would calculate this determinant. What would I get? I would get exactly the same solutions over here, as over here. Because look, when we are actually using cofactors from a wrong row, the situation is identical as we would have two exactly the same rows. So, of course, by the properties we've already learned about, we can say that for sure the value of the determinant must be equal to 0. Again, the proof of this is beyond the scope of this class. But the last thing I want you to remember about this expansion by alien cofactors is that you would always, when you do Laplace expansion by some row, but you use cofactors from a different row, or by some column, and you use cofactors from a different column, you will get 0. Okay, so now the only interesting thing we've skipped about alien cofactors is, of course, what is the formal way of writing it. Okay, again we will use the sum symbol. We are assuming that we have some determinant n by n. And look, we already just, all we need to do is to just we need to use different we need to modify the formula we already had for Laplace expansion. So if we have Ai, J, C, I with us I prime J. So what am I going to do here? I'm using elements from row I, but cofactors from row I prime, and I prime is different than I, I can be sure I'm going to get 0. This is, here, look, here what you see is expansion by elements by row I using cofactors from row I prime. Then I can of course do the very same thing for rows. Here I have expansion by row for columns, expansion by column J by using the cofactors from column J prime. This will also be equal to 0, but of course J must be different than J prime. Look, if it must be different than J prime. If those would be the same, we would have just a regular expansion by a regular Laplace expansion. Okay, and now we've actually covered a lot of ground. We've seen a lot of properties of determinants. But look, finally we are ready to find inverted matrix A, and this is what we're going to do in the next video. Take care.